All right, everyone. The second day of my MOX presentations. We're trying to introduce to you Oscar Garcia-Prada from ICMAT, Madrid. He's going to speak to us about the geometry of Hodge bundles on Riemann surface. Please, Oscar.
Thank you very much. You hear? Yes? That's good. So I want to thank the organizers for the invitation. To speak here is a great honor to be doing something I'm very proud. So I am aware this is a mixed audience, and therefore I should try to be not so technical. And I will sometimes get a bit technical, but I will try to convey the main ideas of this object that I have been interested for many years. It's a theory of the Higgs bundles introduced by Langlands almost 40 years ago. And I want to discuss Hodge bundles are a special kind of Higgs bundles. And I want to do this in the context of any complex reductive group. And so there are many reasons to people are interested in these objects. So moduli is very Higgs bundles with some very canonical object that one can associate with a pair given by a complex Riemann surface and a complex reductive group. And this moduli space has tremendous, tremendously rich geometry. For one thing, it's a hypercube manifold. It defines also a very important integral system. This is the so-called hitching system that plays a very important role in many areas, like in the Langlands program, particularly the group of the fundamental lemma by Rho. And it is also a scenario for dualities and symmetries that are very important, like mirror symmetry, that relate to the moduli space of these bundles for a reductive group related to the moduli space of the dual Langlands group. And also, and this has been a motivation to really be interested in me for many years, is the fact that this space is homeomorphic to the characteristic parameterized representations of the fundamental group of the surface in the given group. Complex or real, in fact, the theory today, I will not be talking about the groups, but the theory of characteristics and using Higgs bundles has led to an incredibly rich subject, which is the emerging subject of higher temperature theory, that is a very active area of research. So today, I want to actually focus on some special subvarieties of the moduli space of bundles that somehow are the skeleton of the moduli space, in the sense that they capture the topology of the moduli space. And these are the Hodge bundles. And so I want to tell you about some new tools that we have developed to study these objects. So let me start by telling you what is a Higgs bundle. So here I consider a compact Riemann surface, G is bigger than 1, the canonical line bundle, the tangent bundle, K. And today I will restrict to semi-simple complex groups, but we could do reductive groups and so on. So consider a semi-simple complex group G. And these are the objects. So a Higgs bundle on the Riemann surface, a G-Higgs bundle, is a holomorphic object consisting of is a pair consisting of a principal G bundle, holomorphic G bundle on X that I call E, and then the Higgs field, which is a holomorphic section of the adjoint bundle. This is the bundle associated to the action of G on its Lie algebra, tensored by the canonical. So these are the objects, right? And so there are appropriate notions of stability that come from geometric invariant theory, Mumford's geometric invariant theory, that allow to construct a quasi-projective variety. So these are the moduli space of some polystable objects defined a the moduli space of these objects. And this is a quasi-projective variety, which is a group with a hyperkiller structure on the two plots, as I mentioned. Okay, so this is, I will give some examples in a minute. So this theory was introduced by Nigel Hitching in 1987, period 1987. And as I said, one of the main motivations to study this space is the fact that it relates in a fundamental way to the moduli space of representations of the fundamental group in G, so homomorphisms from the fundamental group G. And here is again the geometric invariant theory quotient. So there is, to form this quotient, you need to consider representations that have that are completely reduced, let's say, and this gives you a nice moduli space of representations. So here, pay attention to the fact that the Riemann surface structure doesn't play any role. It really is really the. This is actually also a complex algebraic variety, but the complex structure comes from the group G, not so much from the surface. And in fact, this hyperkiller property comes from the combination of the complex structure on the Riemann surface and the complex structure on G. So here is a fundamental one fundamental correspondence in the theory is the non-abelian Hodge correspondence, which establishes a homeomorphism between the moduli space of G-Higgs bundles and the character variety. And this is to prove this correspondence, one actually has to solve two theorems of non-linear keys. I mean, if G was abelian, right, like C star or something like this, then this is just abelian. This is Hodge theory. And to establish this correspondence, we just need to solve a plus equation. But in this situation, when G is generally a non-abelian group that interest, then to establish this correspondence, one has to study some gauge theoretic equations related to Higgs bundles on the one hand here, and in the other side, one has to prove another theorem on non-linear keys that has to do with harmonic maps, and the Ills-Samson theorem, a twisted version of Samson. So there is a lot of analysis in trying to improving this correspondence. Anyway, one of the beauties of having this correspondence is that many people are interested in studying the topology of the character varieties, right? And you can go here and use complex analysis and complex geometry to really tackle the study of the geometry and the topology of this moduli space. Okay, so let me give you a very basic, fundamental example that is that of considering the group, special linear group SLNC, where we can look at these objects in a more familiar way in terms of vector bundles. And so you can do this for any classical group, in SLNC, right? And so we can view a SLNC Higgs bundle as a pair consisting of a holomorphic vector bundle, something more familiar. Because of the special property, we fix the determinant of A to be trivial, trivial length bundle on the Riemann surface. And then the Higgs field here is simply a homomorphism from the vector bundle to the vector bundle tensored by the canonical length bundle. And again, we need to impose the condition that the trace is zero because of the property of this. If we consider GLM, you can dispense from this condition and this one. Now, just for the sake of having some idea of what I mean by stability, in this particular example, stability is coming from geometric invariant theory, is very close to what Mumford introduced for vector bundles, except that now because we have a Higgs field, we check unforced stability condition, but only for some bundles that are left, that are sent by feed. So E prime is sent to E prime tensor K. So this is a condition on the first Chern class of the subbundles, right? And to have an idea what I mean by polystable is this Higgs bundle is a direct sum of Higgs bundles of a smaller rank. All of them with this degree 0 in this particular case, and all of them stay. So this is the kind of thing that emerges from developing invariant theory. This is the first example that was considered actually by Hitchin in his seminal paper. And actually here is a very ruined copy of Hitchin's paper that he passed to me when the paper appeared in 1987. I was visiting Oxford before I became a student there, and I like to. This is a museum piece now for me. I was at the time, so in the summer of '87, I was a student at Rice University in Houston before transferring to Oxford, and so I was 3 months in Oxford. I didn't know that this was going to be so important, of course, but when I went back to Houston, I was a second year graduate student at the NAF, who all geometry group who had a working setting on this thing. And this was a very enjoyable experience. The whole time I was there, Robin Feldman, other people, and we had spent a whole semester dissecting this paper, and I think that was definitely was for me like, and inside this paper there's a whole program I had myself, and it was 10 years. So this is that. Now, so what is this basic fact that I want to emphasize today? And this is a very skeleton of the moduli space. And I continue with this. Is the fact that the C star acts on the moduli space of Higgs bundles by simply multiplying the Higgs field, by scaling the Higgs field. So lambda star, I just take multiply the Higgs field. This is something I can do with this sort of object. I cannot do this with representation. It's something I can do with these objects. And this, now, we can characterize in this particular situation what are the fixed points of this action. Of course, one obvious fixed point is if phi is equal to 0. Right? Then I didn't take that into account. Those are vector bundles. Okay? And so the whole subvariety of vector bundles is inside of this loci of fixed points. But the ones that we're interested in, this is the Hodge bundles, are given by in the following way. You can show very easily that if this is actually isomorphic to E phi, then there's a gauge transformation, and you can decompose the vector bundle in direct sum of vector bundles, and the Higgs field decomposes in this way. Is an important object. These are matrices, and so each of these VIs go from one to the other tensor the canonical. Right? So this is a simple, rather easy computation. Now, these objects, you can see these are in correspondence with what are called twisted chain bundles. So a chain of bundles, meaning just this bunch of vector bundles, E0, E1, En-1, and morphisms. Sorry, I have to say twisted in the sense that each of this is twisted by the canonical length bundle. So this goes from E0 to E1 tensor K. So, right. So these chains have been examined for now already in the paper of Hitchin, the one that I showed, where he considered the rank 2 case, he was analyzing what were the fixed points and was able to extract a lot of information. But so for years, 3 decades, studying these objects, these chains, and a sort of complete study of these objects, meaning the computation of a Grothendieck motif of these moduli spaces, was achieved in work with Johann Langlands and Alexander Schmidt, and where we found a recursive formula to compute the motif, the Grothendieck motif of these moduli spaces, from where you can extract another kind of equation. So, yeah. And the method that, in fact, and so why were we interested in doing that? Is because exactly from the motif of Betty numbers of these moduli spaces of chains, right? We could compute what we want, which is the motif of the moduli space of G by localization, by means of Bielnitsky-Virula localization. And this actually was something that Hitching did in his first paper, and the case of rank 2, and Peter Gotten did later on for n equals 3 using Morse theory. This is another tool that is in the story. Once you are building this moduli space of objects, there is this Hitching equations, and there is a function that is the Morse function. You don't do Morse localization. It's really more algebraic localization. These are equivalent things. I mean, from the Morse localization, you compute Betty numbers, and in the work that I am mentioning with Langlands and Schmidt, we compute the Grothendieck motif. So, the ultimate goal that for years we have been pursuing, many people there, is to carry this program to any group, any reductive or semi-simple group. And it has taken a lot of time to really develop the machinery to study these points. In the case of SLN or GLN, in the vector bundles, so chains of morphism and vector bundles, we can deal with this sort of things, and in a rather sometimes very complicated way. We are dealing with ranks and degrees and kernels and so on and so forth. But for 30 years, we have been understanding this, but without really understanding what's going on. And it's somehow only recently that we came to understand what is the structure that is behind this Hodge bundles, and this the first steps were taken in a collaboration with Olivier Vicard, Brian Collier, and Domingo Toledo in a paper that where we developed, we introduced some basic ingredients to study this Hodge bundles, and the essence of the theory comes from the field that I really didn't know much about some years ago, but it is very important in many areas, is that of pre-homogeneous vector spaces, and in particular, pre-homogeneous vector spaces associated to set grading of simple complex Lie algebras. And the theory of pre-homogeneous vector spaces that was developed by Nikkei Sato and is a incredibly rich theory that has to do with a group acting on a vector space, and the fact that inside the vector space, in this action, there is an open orbit which is the homogeneous space. And these are, there is a very rich, there are no, I mean, so this is a representation of a group, and there are no invariants, but there are relative invariants in the sense that you can find special characters, which you have semi. Anyway, let me explain what I mean by this. And so I consider put myself now in the general situation where G is let's say simple complexly grouped, and a set grading of the Lie algebra is simply a decomposition of the Lie algebra indexed by the integers in such a way that the Lie bracket of something Gi and Gj goes to Gi plus J. And in this situation, there is an element in G0. G0 is a subalgebra, the Lie subalgebra, that is called the grading element. And this grading element actually allows me to tell you that the Gj's are, in fact, the eigenspaces, right, with eigenvalue J. So this is an element in G0, and so this is the decomposition that I have in the Lie algebra, grading element. And so the G0 group is a subgroup that G0 is actually a group with Lie algebra. It's 0, and this is the centralizer. The centralizer, you find the centralizer of this grading element. So this group, G0, acts by the adjoint action on all the pieces here. Right? And here is a fundamental fact proved by Wingberg. That is what I mentioned before, that except the case J equals 0, right, all the others are pre-homogeneous vector spaces for the action of G0, right? Which means that in each of these pieces, there is an open orbit, G0 orbit, that is unique and dense, right? And in fact, each of these pieces has a finite number of G0 orbits. This is a particular special class of pre-homogeneous vector spaces associated to set gradings. Now, let's come back. Now, I want to define for you what is a Hodge bundle using this kind of structure on the Lie. And so I can now, I mean, after this Lie theory and this pre-homogeneous vector spaces, now let's go back to our Riemann surface. And now I want to define some objects that are like Higgs bundles, right? But not quite, in the sense that these are what I call Higgs pairs, where is a principal bundle, but now the structure group of this principal bundle is actually the G0 that I had in the previous slide. And now the Higgs field is in one of the pieces, right? Here, this vector bundle is the associated to the action of G0 on the piece Gi. So these are my objects. And so a G-Higgs bundle, in the sense that I defined before, so this is a G bundle, and phi is in the adjoint, is a Higgs field. Here's the definition, is a G-Hodge bundle of type G0 Gi if it reduces to this kind of pair, meaning that the G bundle E reduces to a G0 bundle, and phi is not taking values in the whole Lie algebra, but actually in this piece. So this is what I would call just a G-Hodge bundle. And why are we interested in these objects is because, and here's the fact that is similar to what I was telling you before for SL and C, is that if we consider the action of C star, that is the action by multiplying the Higgs field, the fixed points are exactly described by this kind of objects. That is, if I have a fixed point, then there is a set gradient in the Lie algebra, and the object, this Higgs bundle, reduces the structure to something like this. So this is the characterization in general terms, right, of what are the fixed points. Now, this much we knew, I mean, for quite a long time in general, right? But what is actually important is that how do we deal with this objects, right? How do we understand the modular space of these objects? Right? And these Hodge bundles are also great relevance because they are in correspondence with variations of Hodge structure. This is via the non-abelian Hodge correspondence. This corresponds to variation of Hodge structure. Now, it is a simple idea that it is enough to deal with the case in which the Higgs field is in the G1 piece. You can always reduce the theory to a situation where if we were in a different piece, we can construct smaller D algebra so that this piece is the G1 of the thing. So this, we will just consider that situation. So the program that we set ourselves was to study the moduli space of these Hodge bundles, pairs of this kind, where you have a G0 bundle and Higgs field takes values in this piece here for any set gradient of the data. Right? And so we wanted to study these moduli spaces. These are the analogs of the chains that I was referring to in the case of SLC. And we want to study the motive of this, and then localization and so on. Okay. So an important fact that is that this moduli, I mean, the moduli space of Higgs bundles, of G-Higgs bundles, is a quasi-projective variety. It's not compact. But these fixed points are indeed projective to some varieties. And one way to see that is the fact that there is another important ingredient that I mentioned in the Hitching vibration. Today, I'm not emphasizing this. Is there is this thing called Hitching mark, and these are actually in this go to zero, the Hitching mark. So by properties, these are compact. So these are projective varieties. Right? G0 is reductive. Yeah, this is just the second I said, right? For this element, right? Typically, not this, sort of reductive, the same. And actually, that we will see when we get from the law. So G was simple, say, G0 for the whatever gradient we have is generally reductive. So G over G0 is in one group. G over G0 is in black. No. You should think of G0. G0 is the Levy. You go back to the gradient. There is a harmonic algebra where you say all the pieces that are bigger than 0. And G0 is the length of all it. So the line that we are referring is actually the quotient of G by the sum B that I'm holding. It just gives the length. Right. So let's put some order here. Yeah. Right. So what in this paper with Olivier Vicard and Brian Collier and Toledo, we developed a theory so associated a fundamental invariant to a Hodge bundle that we call the Toledo invariant, and an inequality, certain inequality to this invariant, that a bound that goes under the name of Arakelov-Milnor bound. And this is something that is a generalization of a theory that had been that is more related, was related to set gradings of this kind, which are set gradings related to real groups of Hermitian type. I'm not going to emphasize this today, but actually Toledo himself, many years back, defined this Toledo invariant and having to do with representations of the fundamental group of surface into a group of Hermitian type, and the real form of Hermitian type is related to this kind of set gradings. And we are actually generalizing this theory to generals. So let me explain what are these objects. This Toledo character and Toledo rank. His author here, he was not very happy when he called this Toledo way out. Now, let's come back to the set grading of Lie algebra. And remember, we have the grading element here, set. And so we can define, using the killing form of the Lie algebra G, we can define a character of the G0, which is this Levy subatomic. And this character is simply by pairing any element in G0 with the grading element by the killing form. And this is indeed a character of the Lie algebra, since G0 is centralized of this grading element. So this is the Toledo character. Now we can define for any element in G1 the rank, and to define that, we complete this element here in G1 is an important element, and we can complete it to an SL2 triple HEF, where F is in G minus 1. Sorry, this is a mistake. H is in G0 and F should be in G minus 1. And once we do that, we can define the rank of this element by applying the character H. This looks like a strange thing. I mean, we're trying to define this, the previous stage of chains. We are rank and so on, ranks of matrices. These are general things. So this is the intrinsically theoretic way of defining rank and things like this. And so the thing is that, as I said, there is the so remember, G1 is a pre-homogeneous vector space, and this meant that there is an open G0 orbit. And we can define the Toledo rank of this pre-homogeneous vector space as the rank of any element in the open orbit. So we have ingredients to Toledo character. It's a character of G0. We have the Toledo rank for any element in G1, and in particular, this allows me to define the Toledo rank of this pre-homogeneous vector space. These are the units. And now, yes, here is another important property of pre-homogeneous vector spaces that plays an important role here, and it's with the regularity of the pre-homogeneous vector space. And this has to do with the fact that in this open orbit, G0 orbit, remember I said this open orbit is a homogeneous space. Homogeneous, the way this pre-homogeneous vector space is a homogeneous space for G0. Quotient is a homogeneous space. Is G0 not the stabilizer of any element in the open orbit? And here the crucial fact is whether this is, we call the pre-homogeneous vector space regular if this isotropicity group is reductive, and otherwise we say it's non-regular. So the reductivity of the stabilizer distinguishes this pre-homogeneous vector space in classes of regular or non-regular. And there is the class of regular ones subdivided in two classes, right? Let me actually perhaps not emphasize this. One is we call JN regular. So then there's Jacobson-Morozov regular. But the key, if you want, the key fact is that this pre-homogeneous vector space is regular if the isochromosome group is reductive, non-regular ones. We need that the isochromosome group is a constant group. Generally non-regular. Okay, so as I mentioned before, one of the basic ingredients in the theory of the homogeneous vector spaces is that the existence of relative invariants. Yeah? That is, that there are like a non-constant rational function that is not an invariant, right? But it is an invariant up to a character. That plays an important role in the theory. For example, if the pre-homogeneous vector space is JM regular, special kind of regular, I mean, let's say regular. There is always this kind of you can exponentiate this the character the Toledo character to a character of the group. Okay, this is getting technical. Let me give you an example. Let me give you an example. And let's go back to the case of SL and C. So these are dealing with matrices and so on. And in particular, the situation where we have this set grading that has three pieces. Here is very explicitly, say, if I take integers P and Q, so that P plus Q is N, here is a set grading of the Lie algebra of SL and C in three different pieces. These are half from CP to CQ, and these are just, this is the G0, right, that I mentioned before, and this is the G minus 1, and this is the G1. And so in this case, the group G0 is actually is the S of GLP cross GLQ. And G1 is this piece here. Right? So these are matrices, and here's the action. The action of here's a representation, right? So if I take a pair of matrices here, and I act on an element M here, this is how it acts. And in this case, the open orbit corresponds exactly to the matrices whose rank is the rank is the minimum of P and Q, and rank is actually rank. The Toledo rank is the rank of these matrices. And regularity has to do with P being equal to Q. If P is different than Q, then the isotropics group is not reductive. And the Toledo character so is actually to a pair of matrices in G0 is just a product, determinant one by the inverse of the other. So these are, in this particular vector function, in this particular SLC case, these are familiar objects, right? We can also express what is this relative invariant in this situation. Okay, so now so what do we do with this Toledo character and so on? And so the thing is that now let's go back to this kind of pair. remember we have this set grading and we have this Hodge bundles. This is a G0 bundle, and we taking values in G1. And the importance of this Toledo characteristic, we can define as value of this term. And the Toledo invariant is actually defined as the degree of this G0 bundle with respect to this kind. So this is the invariant that we attach. And now the Toledo rank that we had defined in Lie theoretic terms for any element in G1, now we can, in the Higgs field, we can define the Toledo rank as the generic. So this Px is an element that is in G1, and it has a generic value, right, for in relation to for generic elements in the Riemann surface. So we define the rank of phi as the generic value of the Toledo rank. Previously, when we were dealing with matrices, these are just the usual ranks, as I said. And so here is the inequality that one can show by exploiting stability of these objects, the geometric invariant theory stability. If this pair is semi-stable, then the Toledo invariant is bounded in this way. Because I was choosing something in G1, the Toledo invariant is negative. If we had been working with G -1, it would be in the opposite sign. This says that this invariant is actually bounded in terms of the genus of the surface. In particular, because the rank of the Higgs field, the largest value is actually the rank of any element in the open orbit, we call the rank of the homogeneous vector space. We do get this absolute bound. Right. Okay, so what can we do with this? Right? What is this good for? And the thing is that all these tools that we have to develop, this inequality and all this will allow us to put our hands in this moduli spaces. And I want to illustrate today this studying the most simple connectedness. And so this is what I want to illustrate today, how we approach the study of connectedness of these moduli spaces, and what are there are other tools that have introduced some kind of secret question that will be very important for connectedness. And so I want to convey the idea that with these tools, we can prove connectedness, we can count the number of connected components. And so the first case we want to consider is, remembering that the Toledo invariant is bounded, we want to consider the maximal situation. Is this modular space also in the theoretical quotient? Does it happen? That's what is of this of modular spaces. Yeah. So one of the difficulties, I said, the program is to study the quality of this spaces section. Some difficulties is the single. So the existence of, say, a universal letter are these are like this slides. These are nice this part. this.
Because for G, you have these size functions. The vertical portion, the G action of the character, right?
Oh, yeah.
Do you have these?
Sure. No, of course, yes. In this part is the character variety, as you said, and G portions. All these moduli spaces in the day are constructed artificially by means of variety. Therefore, we some scheme characterized with objects. Some you have similar shape. It's both there. So whether the model space is defined or not is a very diversity varies. You have this huge and yeah. Right. So we want to study the connectedness of the current connected components. And the first case we want to consider is the one where the Toledo invariant is maximum. That is, has that value. And so what happens is that these are things that one shows is that the maximality of this object implies that the Higgs field takes values in the open orbit for every element in the Riemann surface. This means that basically, after some topological twisting, phi, which was a Higgs field, defines your reduction structure group to the isotropic subgroup of the element in the open orbit. So the Higgs field plays the role of reducing structure. And so all of a sudden, you are left with the Higgs field evaporates in the story. Basically, your pair that was a G0 bundle and Higgs field becomes a bundle whose structure group is this one here. Right? So, one can show that actually the resulting bundle has 0 degree. And so at the end of the day is that in the maximal Toledo situation, this moduli space, strange moduli space that we are studying, turns out to be isomorphic as algebraic variety to the moduli space of bundles, of principal bundles, for a smaller group. Right? So in particular, the number of connected components is actually is in fact the number of connected components of this moduli space of bundles. Now, I didn't mention that we were in the in the regular case, let's say, and remember that in the regular case, what characterized the regular situation was that the isotropic subgroup was a reductive. So this is we're talking about bundles, just a moduli space of bundles. Right? So this is a very familiar object you can understand. We say bundles. So this is something, is a shadow of something that has been studied in the context of which division type and type and A response. Now, so this is how we tackle with the maximum case. If the prehomogeneous vector space is not regular, then it so happens that every non-regular prehomogeneous vector space contains a maximal regular one. And so we can reduce basically to the regular situation. So the maximal Toledo situation, the moduli space turns out to be just a moduli space of one. So this understood. Now, how do we deal with the non-maximal case? How do we deal with the non-maximal case? And so I want to consider now we are dealing with pairs G0 bundle and V and HV and the non-maximal situation. And there is a topological invariant that because we have a G0 bundle, right, is that there is an element in the fundamental group of G0 with the invariant G0. And so I want to fix this invariant. It's like 10 class or something, right? And we fix just inside our moduli space those that have this invariant. And now, the Toledo invariant, we can extract this Toledo invariant out of the topological class of G0. And so here is a conjecture that one has, is that if we have a non-maximal Toledo, then this moduli space is coming. Once we fix the invariant of the G0 value. Now, here is where I promised before that the reductive of the G0 is an important role, because even though we started with a group that was simple and so symmetry serial and serial, and so this is why we do the stability of these numbers. This one the fact that G0 is at something it gives us now a lot of sense for defining stability in the sense of the invariant depending on values. And this is how we see the values. So once we consider these fixed points and we take them away from the natural home of the numbers, then we have independent class. So we have more freedom. There are relations to be depend on electron zero. Some can be said with respect to and so on. So we have this this parameter are importance in the story. And what are these parameters? So these parameters have to do with elements, as I said, in the center, basically, of T0. And so, more concretely, we consider in this the algebra, this algebra, T0, a maximal complex algebra. And these parameters are elements in the center. And so there is, this center can be very big, but it's enough to study connectedness to consider a multiple already having a line that is a multiple of the grading element. The grading element is in here. So we can take a line of this grading element. And this will give us enough space to study these multiple spaces. And so in the case of this, kind of gradients, right? When the group is, the starting group was simple, actually this is one dimension. And there is indeed this, what we call the Toledo line, right? That has been much exploited to study character varieties. In this general situation, there are many, the space of parameters is larger, but it's enough to consider actually, as I say, this Toledo, meaning parameters that are just multiple of the grading element. What one has as an element of the moduli is lambda 0. Here we are taking now any lambda, any real lambda. And the fact is that the Milnor, the Arakelov-Milnor inequality that one has is actually more general. There is this more general Arakelov-Milnor inequality that involves this parameter. And so then what we can do now is take advantage of this parameter. And so what we do is we fix the Toledo invariant of our objects. Remember, we want to study the connectedness properties of the moduli space of that kind of Toledo invariant. And what we do is we fix it, and we instead consider how things vary with this parameter. And we found that this parameter that we have to add is most boundary. Actually, it's the same these are the Arakelov-Milnor inequalities, but instead of just the previous situation, we were finding the inequality for the Toledo invariant. Here we are fixing the Toledo invariant, and instead we are considering parameter, right? And so then the steps in the proof of the conjecture that was proving that in the non-maximal Toledo, which we expanded, is there are several steps in the program, and one step is studying movements of these moduli spaces as lambda. We want to get lambda equal 0, but we study lambda equal 0. Then we take advantage of this parameter, considering a large value of the parameter. And then we realize that this parameter, this is a very sort of typical phenomenon in GRT. This there is chambers in the parameter, and so there are some finite number of values where there are changes in the moduli spaces, and so we need to analyze what happens if we cross this values, and then we, as I say here, walk on the Toledo line from lambda bigger than 0 until we get to 0, which is the value we're interested in. And we don't go to lambda less than 0. Here, things are pretty wild. In this case, put in that here. That is the territory that we don't understand. We don't need to understand. So, just because time is mounting, let me say that this program we are carrying out with John Heimler and Brian Collier, and let me just quickly explain. Yeah, so these are some of the one of the important bits is the characterization of this moduli space when the parameter is large, and the fact that this is a connected space, and all this program of crossing and so on can be carried out. We have done that so far in the non-regular case. The regular case is more difficult and involves some type of new Hecke transformations. Very familiar effect on theory, that in this particular situation, Hecke transformations are adapted to the structure of pre-continuous vector space, and we are still dealing with that. Right? So this is this is all very technical, but I just want to convey the idea. The theory of the vector spaces of the spaces of associated gradings that we have it's just incredibly adaptive the study for ones. And it's something that when people are dealing with Langlands and so on, we do how types of bundles, classes, that in the force with incredible decades of work. Now we understand that there is a beautiful structure of this imbalance. So, yes,